In this video, we're going to be going over titrations and just what's involved when a titration is conducted, as well as calculations involved in titration experiments. So a titration is a common experimental design which is used to determine the concentration of a substance in solution. A titration involves a continuous and progressive addition of a solution, which is called a titrant. Which is coming from the burette. And it goes into a precisely measured volume of a solution, which is called either the sample or the analyte, which is your solution that you don't know the concentration of. So your sample is going to be put in an Erlenmeyer flask. Okay, and you'll see an example of what an Erlenmeyer flask looks like on the next page there. So this addition occurs until a color change or an endpoint, so that's a key word that you should know, is reached. Okay, so the color change, that point is called the endpoint, and the volume of the titrant added to reach the endpoint is often called the equivalence point. So that's another term that you need to know. So the equivalence point refers to how much volume of your titrant that you've added. A burette allows for a precise and accurate measurement and control of the addition of the titrant to the sample found in the Erlenmeyer flask. And before performing a titration, you must know the concentration of one of the solutions, which oftentimes that's going to be the solution in the burette that you know the concentration of, to a very high certainty, since all stoichiometric calculations will be based off of this value. The solution with a known concentration is known as a standard or standardized solution, and a standard solution can be prepared from either a solid or by dilution, and this is known as preparation of a primary standard, when you either create that standard solution either with a solid or by dilution. Now, when you're conducting a titration, usually you do more than one experiment or more than one trial. And what you need to do is you need to repeat your trials until you get 3 trials where the volume of titrant added are within either plus or minus 0.2 milliliters. Okay, so for example here, let's say we added enough titrant so that for one trial, let's say we added 34.31 milliliters of titrant. So we would need to get 3 trials that are within or from 34.11 milliliters, and we could go all the way up to 34.51 milliliters. Oh. Okay, so this is just saying this would be the range that would be acceptable for your 3 trials of your titration here, because this one is the minus 0.2 milliliters and this one would be plus 0.2 milliliters. Okay, now just as a heads up, when you're reading how much titrant you've used, you always go to 2 decimal places. So let's make sure that we write this down. Okay, so oftentimes you end up estimating the very last digit. So the very last digit, what I mean by is these ones here. Okay. So with reading a burette, to read the volume, you always go to the bottom of the meniscus. Okay, so the meniscus is this curved line that will show you the level of your titrant. Okay, and you always read to the bottom of it. So in this case, this is showing that we have a volume of 23.45 milliliters. Okay, so each one of these tick marks here is 0.1 of a milliliter. Okay, and since the meniscus is in between these two tick marks there, that's why we can go 0.4 because it's 1, 2, 3, 4, and then it's halfway in between the fourth tick and the fifth tick. So that's why we've estimated it to 23.45. So just estimating that last digit there, that 5. Okay. When you're reading a burette, the somewhat longer tick marks, that just denotes that that's the halfway point. Okay, so, or like 0.5. Okay. So this is just a picture showing a pipette right here, which they're attaching a pipette bulb, which is how you would get a measurement of that's very accurate of your sample, and you would use that to put that into the Erlenmeyer flask, which is this flask right here at the bottom. Okay, and in the Erlenmeyer flask, what goes into it is going to be your sample, or if you want to call it your analyte, you could call it that too. But this is what you don't know the concentration of. So sample solution, I'll write solution underneath actually. Which is an unknown concentration. And you're also going to be putting your indicator. Okay, so as a quick reminder, an indicator is just a weak acid that changes color based on the pH of the solution that it's in. Okay, some other parts of a titration setup, which is shown here on the right, is the long stick part. So this part right here, that is the burette. And inside the burette, that's where your titrant goes. Okay, so this is a substance that you know what the concentration is. And you know it to a very high degree of certainty. Okay, and oftentimes when we see calculation problems, you'll know that a substance is your titrant when you see the words like titrated with. Okay. The brown thing that's kind of holding up the burette, that is a burette clamp. And the burette clamp is on something called a ring stand. Okay, so the ring stand is just this rod as well as the platform that it's on. Okay. Last but not least, for the burette, the part of it that's going to control how much liquid goes through is going to be this part, which is called the stopcock. Okay. So just another example of reading a burette. Sometimes what's confusing about burettes is that the smaller numbers are up here near the top, whereas the larger numbers are near the bottom. Okay, so sometimes that's a bit confusing. So with this volume here, how you would read it is you'd be like, okay, first locate the big number, which is 39 milliliters. Okay, and then let's count how many tick marks we can go down until the very bottom of the meniscus. I'm trying to draw a straight line here. It's not going so well, but let's go right there. So 39 and then 0.1, 0.2, 0.3, and it's a bit past 0.3. So they've estimated the last digit to be 1. Okay, so that's how they're reading this, as 39.31 milliliters. Actually, before we move on, let's just write ourselves a little note. Okay, measure titrant. I've said this, but I just haven't written this down. Measure titrant. And you'd be at eye level if you were in the lab. So at eye level. And you need to measure from the bottom of the meniscus. All right. Let's get on to our first example here. So we have vinegar is conveniently analyzed by titration with sodium hydroxide. Complete the analysis of the investigation report. So the problem is, what is the concentration of acetic acid in a sample of vinegar? For our experimental design, several 10 milliliter samples of acetic acid are titrated with. So this is the key words that I was mentioning here, that when you see the words titrated with, that's going to be referring to your titrant. So that's what I was trying to say right here. The words titrated with, those are your key words to say, like, whatever comes after that is going to be your titrant. So it's titrated with a solution of sodium hydroxide. So this right here is going to be your titrant. Okay, and we have 10 milliliter samples of acetic acid. So since they're samples, right, that's going to be what you don't know the concentration of. So unknown concentration. This is what you're trying to find. Meanwhile, the titrant, you know the concentration of that. Okay. All right, so part of the trick of these questions is being able to figure out what your titrant is, so what you know the concentration of, as well as the volume of it. And you also need to be able to tell that apart from your samples, which you don't know the concentration of, but you will typically know how much volume you are using of your sample. Okay, so we'll come back to that later. Phenolphthalein was our indicator, which changes from colorless to pink at the end point of the reaction, and it's used to detect the equivalence point. All right, so in titration questions, typically you get 4 trials, and you need to figure out, okay, which trial do I need to omit? Because we only need 3 trials that are within plus or minus 0.2 milliliters. Okay, so right now what we need to do is we need to go through all of these trials, and we need to figure out how much volume of titrant we used. Okay, so they've given us the final reading as well as the initial reading, and how you figure out how much titrant is used is you just subtract initial from your final. Okay, so you're just subtracting here. So 14.8 subtracted by 0.7, that's going to give us 14.1 milliliters. Let's do the same for trial number 2. So 26.9 subtract 13.9, that's going to give us 13. And these are all milliliters. Okay, 39.8 subtract 26.9, that's going to give us 12.9. And then trial number 4, 13.6 subtract 0.5, that's going to give us 13.1. Okay, so as you can see, these trials here are all kind of pretty similar, and this one is our outlier. Okay, so if we said, or if we looked at trials 2, 3, and 4, we could say, okay, 13's in the middle, and 12.9 and 13.1, they're within 0.2 milliliters of 13. Okay, but just so that you're aware, we could accept any numbers between 13.20 down to 12.80. Okay, so that's our range of acceptable answers that we can keep in our calculation. However, trial 1 is an outlier, so we shouldn't use that because that is going to skew our calculations. That's why we need to omit it. Another way that you can tell that trial 1 is an outlier is because notice how the color at the endpoint here is dark pink, whereas for the rest of them it's light pink, which is what we want when we're using phenolphthalein. You want this very faint pink color. Okay, so again, you only use 3 trials that are within 0.2 milliliters of each other. So let's just write that as a little note here. All right, so with this is ultimately going to be a stoichiometry question, and it's going to be a solution stoichiometry question. So we're going to go back to our 4 steps of solving stoichiometry questions, which I'm just going to write out quickly here. Okay, so our 4 steps are: step 1, write a balanced chemical equation. Step 2, find the moles of your given substance. Step 3, use a mole ratio to convert your moles of your known substance to the moles of your unknown substance. And then step 4, answer the question. Okay, so take your moles of your unknown substance and convert it into whatever the question's asking, whatever units the question's asking for. All right, so let's work on step 1, balanced chemical equation. Okay, so we've been told that we're working with acetic acid and sodium hydroxide. Okay, so let's start off with what we know, which is sodium hydroxide. Sodium hydroxide, and that's a solution. Okay, because both of these, both acetic acid and sodium hydroxide are solutions here. And let's see, they don't give us the formula of acetic acid, but that's no worries. We can look it up in our data booklet. And that is going to be on page 8 and 9. Okay, so with page 8 and 9, it's going to be telling you a bunch of acid names. So essentially we just need to scroll through and see where acetic acid is. Okay, so I'm finding acetic acid right here. So that means that the formula for acetic acid is going to be CH3COOH. So if you're looking for an acid formula, you might need to look on page 8 and 9 of your data booklet. And that's going to be aqueous because acids are always aqueous. All right, so since we have a strong base reacting with a weak acid, that's why I'm using a single arrowhead. Another reason why I'm using a single arrowhead is because this is a stoichiometry calculation, so one of the assumptions that we make is that this reaction goes to completion. All right, now we need to figure out, okay, what kind of reaction is happening here? So we have a compound reacting with a compound, and that is going to be a double replacement reaction. Okay, now the key with acetic acid is that there's a special hydrogen, okay, which is this one right here, that is going to be considered our cation or our positive ion. Okay, how you would know this, just because you don't have to memorize this, but how you could figure this out is you could go back to page 9 of your data booklet and look at the conjugate base formula of acetic acid and be shown, oh, okay, that's your anion or that's your negative ion. So then the last hydrogen at the end of this formula has to be your cation. Okay, so I'm going to just color code my cations here, and let's color code sodium because that would be our cation there. All right, so double replacement reaction, you could either think of it as your cations are going to switch places or your anions are going to switch places. Okay, pick one strategy and stick with it. I personally like just switching my cations. So sodium and hydrogen, they're going to trade places here. So what I'm going to get for my first product is going to be water, which you can write as H2O, but I'm just choosing to write as HOH here. Water is going to be a liquid, it's never aqueous. And for my second product here, we're going to have sodium as well as the acetate ion. So the acetate ion is CH3COO, and then we got sodium here. So if you're wondering why I've written it this way and wondering if you could write it the other way, like this, so that cation always comes first, yeah, you could. Okay, either or is acceptable here. And you know what, just to go with consistency with the positive ion always coming first, I'm actually going to stick with the second one here. All right, now let's check the solubility of sodium acetate, which is this thing right here. So let's go to our data booklet, go to our solubility table, and you'll find the acetate ion right here. Most things are soluble, but let's just double check that sodium acetate isn't here. It's not, so therefore it is going to be soluble. So we rate it as aqueous. Okay, now let's just make sure that each of our compounds are balanced. So hydrogen has a +1, hydroxide has a -1, water is balanced. Sodium has a +1 charge, acetate has a -1 charge. That's a balanced compound as well. So we're good to go on this front. Okay, so right now we have our skeletal equation. Let's just make sure everything's balanced. Okay, so we have 1 sodium coming in, 1 coming out. 1 hydroxide going in, 1 coming out. 1 acetate ion going in, 1 coming out. Okay, and then 1 hydrogen going in, 1 hydrogen coming out. Everything's balanced. All right, so let's organize the information that we've been given. Okay, so going back to the experimental design, it says several 10 milliliter samples of acetic acid. Okay, so that word of connects this volume with acetic acid. So let's find acetic acid and say, okay, our volume is going to be 10 milliliters. Okay, and looking at my notes here, since acetic acid is the sample, that's what we don't know the concentration of. That's what we're trying to find. So I'm going to go concentration is equal to question mark. And actually, I'm going to leave a bit of a space here. The reason being is because concentration is moles per liter. If we look at our volume, it's in milliliters. So we're going to want to convert it to liters. So I'm just going to get that done and out of the way. So going from liters to milliliters, writing out our metric conversion line. Okay, so milliliters is going to be right here. Liters is going to be right here. It's a base unit because it doesn't have a prefix to it. So I count 1, 2, 3. So to convert from milliliters to liters, I need to move the decimal 3 to the left. So 1, 2, 3. So it's going to be there, and I'm going to have to put in a 0. So cleaning that up, it's going to be 0.01 milliliters. Or, sorry, liters. All right, so that's taken care of. Now let's move on. So acetic acid, volume of it, we took care of it. Okay, acetic acid is titrated with a standard 0.202 mole per liter solution of sodium hydroxide. So let's put that in. So concentration is 0.202 mole per liter. Now for the volume, we figured out what the volume of sodium hydroxide was by doing these trials. Okay, but remember, we're not counting the first trial because it's an outlier. And what we need to do is we need to find the average of the 3 trials that we are going to accept. Okay, so I'm going to call this volume average. So how you find an average is you add up each of your numbers and then divide it by how many terms you have. So we're going to add all these numbers up, and then since we have 3 numbers, we're going to divide it by 3. So 13 plus 12.9 plus 13.1 divided by 3. So let's get out our calculator. Hit enter, divided by 3, that's going to give us 13. So that's 13 milliliters. All right, so we've organized our information. We have our balanced chemical equation. Now we're going to move on to step 2, which is find the moles of your given substance. So the substance we have the most information for is going to be sodium hydroxide, so that's where we're going to start. Okay, now in order to find the moles of sodium hydroxide, we got to think, okay, what formula uses concentration, volume, and moles? So let's go to our formula sheet. And if I look, this formula here deals with concentration, volume, and all we need to do is isolate moles in order to figure it out. So that's what we're using. So concentration is equal to moles divided by volume. We want to isolate moles, so we got to ask ourselves, okay, what is volume mathematically doing to moles? Well, it's dividing, so the opposite is going to be multiplying. So these cancel out, and we're going to be left with volume multiplied by concentration is equal to moles. That's what we're using. All right, let's see how much room I have. I think I'm going to have to scooch this up a little bit. All right, so with this, one thing that we need to be mindful of, which I was mindful of here, but not over here, is that our units for volume is milliliters. How I know that for sure is because that's what the question tells us. It's all in milliliters. So we're going to have to do the same thing that we did over here with the volume of acetic acid, and we need to move the decimal 3 over to the right. So let's get that done before we keep on going on with our calculation. So 1, 2, 3. There we go. Have to put in another 0. So it's 0.013 liters. All right, so looking at our formula, moles is equal to volume, which is that 0.013 liters, times by concentration, which is 0.202. So liters is on the top and the bottom, they cancel out. Now let's put this into our calculator. Okay, so let's get rid of that 0.013 times by 0.0202, sorry. So we get 0.002626. Actually, I don't think that number keeps on going on. My bad. Okay, and that's going to be moles of sodium hydroxide. The reason why it's sodium hydroxide is because we use the concentration of sodium hydroxide as well as the volume of sodium hydroxide. So that's why these moles belong to sodium hydroxide. All right, so that's step number 2, done. Step number 3, that's mole ratio. So let's use a different color here. So mole ratio times by a fraction sign. What you want goes in the top. What you've been given goes in the bottom. So we were given sodium hydroxide. We want acetic acid. Okay, and the coefficients for both of these are just 1. So that's just going to give us the same number. However, now these are going to be the moles of acetic acid, because if you treat sodium hydroxide kind of like a unit, you see how sodium hydroxide's in the top and the bottom, they cancel out. So that's how we know, okay, these moles now belong to sodium hydroxide. And I'm going to write mole right there. Actually, hang on. Let's see if I can squish this over. Oop. There we go. Okay. At this point, we've got step 3 done. Step 4, answer the question. Okay, so the question ultimately is, and I've written it out here, but also you can find it in the problem, what is the concentration of sodium hydroxide? Oh, it did give us the formula in the end. Oh well, now you know how to find the formula for an acid in a different place in your Chem 30 data booklet. All right, so we need to figure out what the concentration is. So I'm going to go back to that formula that we started off with here. This concentration is equal to moles times volume. The reason why I'm going to use this is because we just figured out moles of sodium hydroxide. And if we look back at the question here, we already have the volume of acetic acid. So let's go back. We have the moles of acetic acid and we have the volume of acetic acid. We just need to figure out the concentration of it. Okay, so concentration is equal to moles divided by volume. And I'm just going to have to put that underneath here. So let's just move this. Oop. Concentration, moles divided by volume. So we got 0.002626 moles divided by, so our volume. So remember, moles of acetic acid has to go with volume of acetic acid. The volume was 0.01. And let's divide that. So that's going to give us 0.2626. And that's moles per liter because no units canceled out. All right. And let's add in acetic acid. Okay. Let's look at our numbers given. This is in 4 sigdigs, so the 10 milliliters, that's in 4 sigdigs. This is in 3 sigdigs, so it looks like we should be going with 3 sigdigs here. So if I'm counting from the far left, remember leading zeros do not count as sigdigs. So 1, 2, 3, there's my cutoff line. So 3 sigdigs. So that's going to be 0.263 mole per liter. And I'm going to erase this part here. Mole per liter of acetic acid. Okay, so this next question is going to be very similar here. So the problem is, what is the molar concentration? So molar concentration and concentration, they are the same thing. So what is the concentration of hydrochloric acid in a solution of kettle scale remover? Experimental design, the hydrochloric acid in a solution of a kettle scale remover is titrated with, so there's our key word, titrated with a standard solution of barium hydroxide. Okay, so this is going to be our titrant. We know the concentration of that, which I'm going to abbreviate concentration just to CONC. The color change of bromothymol blue indicator to green indicates the equivalence point. Okay, so here, another easy way to kind of figure out where to organize your information would be like just this heading here. So it says titration of 10 milliliter samples of hydrochloric acid. So that word of connects the 10 milliliters to hydrochloric acid with, so this is titrant, or words that indicate that the substance that comes after is going to be your titrant. Okay. So 0.974 mole per liter of barium hydroxide, that's our titrant. Okay, so we're going to do the exact same process, which is calculate how much titrant, so barium hydroxide, we used for all 4 of these trials, figure out which one of them is going to be our outlier, although right now I'm sure you can see this first trial has a different color than the other one, so this is likely going to be our outlier. Okay, but let's just go ahead and figure it out. So this is 15 milliliters. Subtracting these two is going to be 13.7 milliliters. Subtracting these two is going to be 13.7. And then subtracting these will be 13.6. Alright, so as you can see, these trials are all within plus or minus 0.2 milliliters. This is our outlier, so we are not going to use it. Alright, so we're reacting hydrochloric acid with barium hydroxide. We can use that to set up or start setting up our balanced chemical equation. So hydrochloric acid reacts with barium hydroxide. Nope. Okay, so what we have here is we got a compound reacting with compound, so it's a double replacement reaction. So once again, I like to just see it as switching my cations. So I'm going to switch my hydrogen and my barium. So my first product here, that's going to be barium chloride. Now barium has a 2+ charge. Chloride likes to have a -1 charge. So obviously 2 minus 1 does not equal 0, so we got to do crisscross applesauce. So that's going to cause it to be like this. I will worry about the state later. Okay, my second product is going to be hydrogen going with hydroxide. So when you're writing your products, the subscripts do not come along for the ride. The subscripts, the whole point of them is only to balance out the compound. Now since that's water, and we know that it's easiest to just look at this as hydroxide and hydrogen. So hydrogen has a +1 charge, hydroxide has a -1 charge. So that's balanced already. And that's a liquid. Alright. Let's see what the state of barium chloride is. So chloride is right here. Most things are soluble, but let's double check. Barium is not here, so it is soluble. Okay, so right now we have a skeleton equation and we need to balance it. So I've got 1 hydrogen going in, and right now I'm just counting this as a hydrogen and then this as a hydroxide, okay? So I've got 1 hydrogen going in, 1 hydrogen coming out. So those are balanced. But I've got 2 hydroxides and only 1 hydroxide here. So I'm going to put a 2 right there. Okay, so the 2 didn't just affect hydroxide, also affected hydrogen. Now let's just go back and make sure we got 2 hydrogens going in because there's already 2 coming out. Okay, so the 2, we've balanced out our hydrogens, but the 2 didn't just affect hydrogen, also affected chloride. So we got 2 chlorides going in, 2 chlorides coming out, that's good. 1 barium going in, 1 coming out, that's good. So everything is balanced now. Alright, let's organize our information. So we've got the titration of 10 milliliter samples of hydrochloric acid. So volume of that, 10 milliliters, but you're going to want to convert that into liters And as we said before, you just need to move the decimal 3 to the left. 1, 2, 3. So that's going to be 0.010 liters. Okay, or if you don't have to write this 0 right here, you could just do that. Okay, but since hydrochloric acid is our sample, that means we don't know the concentration of it. Another way to figure out what you don't know the concentration of is because it says, what is the molar concentration of hydrochloric acid? So let's go concentration underneath hydrochloric acid. We don't know. Okay. Barium hydroxide. So we know the concentration of it because that's our standard solution. So let's write that out. Concentration 0.974 mole per liter. And with our volume, this is where we're going to find the average of the 3 trials that we are accepting because they're within plus or minus 0.2 milliliters. Okay, so we've got, actually, let me fix this. Average is equal to 13.7 plus we had 13.6 divided by 3 because we were doing 3 trials. All right. So 13.7 plus 13.7 plus 13.6. Enter, divided by 3. It's going to be 13.6 repeating. So I'm just going to do to 4 digits after the decimal. I'm going to write a line over top that just means the 6s keep on going on forever. And that's milliliters. But I'm going to convert this to liters. Just because I know I'm eventually going to have to do that to cancel out with these liters here. So once again, we're just moving the decimal 3 spots over to the left. So the average is 0.01366. This goes on forever, liters. Okay, now the important part is that we're not going to round off this number. We are going to keep the raw number and use it in our calculation. So do not round a number off early in your calculations. You only round when you're giving your final answer. Okay, so step 1, balanced chemical equation, done. We organized our information. Now we need to do step number 2, which is find moles of our given substance, which in this case, we're given the most information for barium hydroxide. Okay, so as we said before, okay, we can find moles using this formula. So moles is equal to volume times concentration. So the volume was that times by that 0.974 mole per liter. Liters cancels out. And let's see what this equals. So I'm just going to divide this by 1,000. That'll give us our same number. And then times it by 0.974. So our answer here is 0.1331, goes on forever. And that's our moles of barium hydroxide. Okay, so that's step number 2, done. Step number 3, mole ratio. So times by fraction sign. What we are given goes in the bottom. What we want goes on top. So remember, we're looking for the concentration of hydrochloric acid. So the coefficients, there's a 2 in front of hydrochloric acid, and there is an invisible 1 in front of barium hydroxide. Okay, so what we're doing is we're taking our moles of barium hydroxide, we're multiplying it by 2. Okay, so we're going to get 0.02662 goes on forever. And these are now the moles of hydrochloric acid. Now, the question's asking us, what's the molar concentration of hydrochloric acid? And from our previous question, this is the formula we use. Concentration is equal to moles divided by volume. That's what we're going to do here. So, taking that unrounded number of 0.0266 goes on forever moles divided by, so moles belonged to hydrochloric acid. Volume also needs to belong to hydrochloric acid. So the volume was 0.01. So that's going to give us 2.662 goes on forever. And that's moles of hydrochloric acid. Now, let's look at our question here. So, 10 milliliters, that has 4 significant digits, but the concentration of barium hydroxide, that only has 3, so we're going to go with the lower amount of sig digs. So this needs 3 sig digs. So counting from the far left, 1, 2, 3, there's my cutoff line. So 2.66, oh, that should be mole per liter. Mole per liter of hydrochloric acid.